we have a semicircular wire. It carries a current I and it is put on a uniform magnetic field B. We will calculate the magnetic field, the magnetic force on the straight part of this loop, which carries a current I to the positive x direction. And also we will calculate the magnetic force on the semicircular part. So let's call these forces on straight part as F1 and the semicircular part as F2. And let the magnetic field B be expressed in the unit vector notation B times J, the unit vector in the y direction. And we just write down the magnetic force F1 on the straight wire by using the formula the current times the length vector of the current S cross product with B, the magnetic field. And I think I have to put the error sign in here. So we will write down these vectors in explicitly. S is just 2 times the radius of the circle. The radius of the circle is given as R. And since the current is in the direction of the positive x-axis, we put the unit vector I in here. 2R times I is the S vector. And this will be cross product by the magnetic field B, and it's B times J, and B is constant. So next, we take just the cross product of the unit vectors I and J, and this is nothing but K, and the result is 2 times the current I times the radius of the semicircle and times the strength of the magnetic field, and the force will be in the Z direction, positive Z direction, which is outward to the plane of the board. Next, we will calculate the magnetic force on the curved part of this current loop, and the curved part is in the shape of a circle. So for this, we can decompose this semicircle part into small sections, which we call ds, and we will write down the magnetic force on each small sections ds as df, right? And we will express first this df2 in terms of the infinitesimal length vectors of ds's and the magnetic field, as in this expression I times ds cross the magnetic field is just the magnetic force on any small section of this semicircle. And for this, let's think of this arbitrary small section ds, and from the center we have this r vector, the radius vector, and since ds is infinitesimally small, this defines an infinitesimally small angle through the center of the circle. And we also measure in the polar coordinates the angle of this radius vector, which points to the starting point of ds as theta. And let me show these vectors in a different picture. And this is the r vector, and this makes an angle theta with the x-axis, and this is the infinitesimal small ds, and which is perpendicular to the r vector. By the way, this ds, small ds vectors sections are always perpendicular to the radius vector to the center of the circle. So let me decompose next this ds vector into x and y components. By using the geometry, you can decompose this ds vector into x and y components as this. Since this angle is theta and this angle between r and ds is 90 degrees, you can easily figure out that ds makes an angle theta with the y-axis. And the rest is easy to express dxx and dsy in the x and y directions by using the length of this arc, because ds is just the arc length, infinitesimal arc length of the semicircle. And let me write down this as a vector component, dxx and dsy, I and j. So I will just write down dsx as the length of this infinitesimal arc length times the sine of the angle theta, because dsx is pointing toward the negative x-axis, and we have to put this minus sign. That's why we have to put the minus sign in here. So the arc length, ds, times sine theta, and it is in the minus x direction, minus I, is just the x component, and similarly the y component is just the arc length, ds, times cosine theta, and j is the unit vector in the y direction. So next is, what is ds, the arc length? And we all know from geometry that any section or arc of a circle is just the radius times the angle that sees this arc length, and this we call d theta. So ds can be written down as the radius of the semicircle r times d theta. So let's put everything in the formula, and since now we can write ds as unit vectors, and we know what b is in terms of the unit vector j. So when we write down explicitly all the terms, we immediately see that the infinitesimal force on the infinitesimal arc length of the semicircle is nothing but this minus I, the current, times the strength of the magnetic field B, times the radius of the semicircle, times sine theta, d theta, and it is all in the z direction. But since we have minus sign in here, the force on the direction of the force on any section of this semicircle is pointing the negative z axis. So next is, since this is just only infinitesimal part of the force, we have to take this integral to find the total force on the semicircle. And to find the total force, we just take the integral of this expression. As the variable we have theta, and we know that theta runs from 0 to pi, right? Because this is a semicircle and it runs from 0 to pi, and the only expression which depends on theta is sine theta, and when you take this integral, it's easy to find the result. The total force on the semicircle curved part only is nothing but minus 2 times the current I times the strength of the magnetic field times the radius of the semicircle, and k is the unit vector. So you just see that this result for the curved part of this loop is just the negative of this force which is on the straight part of this loop. And we all know that a closed loop which is put into a uniform magnetic field experiences no net force. So this is just the verification of this result, that the total force on this loop when you add is equal to 0. So just verify that by just calculating explicitly the forces on the curved part and the straight part and adding them together, we get a 0 net force on any closed loop of current which is put in any, this result is true for any uniform magnetic field.